Our homework last night, everyone, from page 683, 1 to 2, 8 to 20, had some requests to do question 13, 14, 15, 17, and 18C. So let's take a look at question number 13 here first. It says, a ray of light traveling in water approaches the water-air boundary at an angle of 50 degrees. What happens to the light ray at the boundary? So we're not necessarily looking for an angle of refraction here, although you could have calculated that. They're only looking for kind of a qualitative analysis of what happens here. This light ray in water approaches a water-air boundary. So let's draw it out, see if we can figure out what happens. It's in water. It's going to the water-air boundary. What's going to happen to that ray? In other words, let's see, which way is it going to bend? Is it going to bend toward the normal line, or is it going to bend away from the normal line? Is the angle of refraction going to be bigger than the angle of incidence, or is it going to be smaller than the angle of incidence? It's going to be bigger, yeah. It's going to be a bigger value. And the reason it's going to be a bigger value is because the index of refraction of water is greater than the index of refraction of air. Here we've got 1.33, here we've got 1.00. If that's the case, then it's going to speed up. As it speeds up, the angle of refraction is going to be bigger. Now, one thing that just occurred to me literally as I was going through this and kind of thinking about it as we were doing it, because it's bending away from the normal line, there's a possibility of total internal reflection happening here if we're above the critical angle. So what we should do here actually is calculate the critical angle so that we can completely answer this question correctly. If we're above the critical angle, then the correct answer to this question would be, it doesn't refract with a bigger angle, it actually reflects. If we're smaller than the critical angle, then we're just going to say that the angle of refraction is bigger than the angle of incidence. Let's calculate the critical angle here for number 13. Let's say that sine theta c over sine 90, which is just 1, is equal to n2 over n1, which is 1.00 over 1.33. This disappears because it's equal to 1. We find theta c, it's equal to the inverse sine of 1 over 1.33. Does anybody have a value for that? Did anybody calculate the critical angle there? 48.8. Okay, interesting. Okay, so when I looked at this question first, I thought, okay, it doesn't seem to be, a quantitative question. It just seems like they're asking, what happens to it? Oh, it bends away from the normal line. But because total internal reflection is possible when you're going from a high to a low index of refraction, we got to find out whether that actually happens or not. And sure enough, it does. The critical angle is 48, and we're at 50. It's going to reflect. So we got to change this diagram a little bit. It's not doing this. It's doing this. Just out of curiosity, if our angle of incidence is theta 1 and our angle of reflection is theta 2, not refraction anymore, but reflection is theta 2, what's theta 2 going to be? What's the value of the angle of reflection going to be? 50 degrees, because the law of reflection kicks in now, right? Where the angle of incidence equals the angle of reflection. All right, 14 says, light with a wavelength of 540 nanometers enters a ruby crystal with an index of refraction of 1.54 at an angle of 25 degrees. What's the angle of refraction and the wavelength of the light in the ruby? Let's draw it out. Okay, we're entering the ruby crystal, so we'll say this is ruby down here, and it has an index of refraction of 1.54. It's entering at an angle of 25 degrees, and that 25 degrees is always going to be measured from the normal line. We're going to call that theta 1. The angle of refraction and the wavelength of light in the ruby, we're going to assume that it's coming from air. It should say that, but it doesn't. We're going to assume that it's coming from air that has an index of refraction of 1.00. Tell me what's going to happen to the speed of this light as it goes into this new medium ruby. Is it going to speed up or is it going to slow down? Going from air to ruby, you don't even need the indices of refraction here. You know what's going to happen to it, right? When it goes into ruby from air, it's going to slow down. It has to, because it travels as fast as it possibly can in air, almost, other than a vacuum. So it's got to slow down. But we also know because the index of refraction is getting bigger, the speed is getting smaller. It's going to bend like this. We're looking for theta 2 here. And theta 2 is going to be a value that's smaller than theta 1. We're also going to look for the lambda 2, which is going to be a value that's smaller than lambda 1. If speed gets smaller, then angle gets smaller, as does the wavelength get smaller. Let's say sine theta 1 over sine theta 2 equals n2 over n1. We're going to say sine 25 degrees over sine theta 2 equals 1.54 over 1.00. So that 1 just disappears because 1.54 divided by 1 is still 1. Still 1.54. Let's take the sine theta 2 up by multiplying, the 1.54 down by dividing. Let's calculate the number on the left-hand side, and then let's take the inverse sine, or the second function sine of that. What do we get when we take the second function sine of sine 25 over 1.54? 15.9 degrees. We predicted an angle that was smaller than 25.0 degrees, and sure enough, we ended up with a value that was smaller than 25 degrees. Now let's find the wavelength here. Let's say lambda 1 over lambda 2 equals n2 over n1. Once again, we're looking for lambda 2 here. Lambda 1 is 540. Do we have to convert that to meters? We can leave that in nanometers here, right, as long as we recognize that our final answer will also be in nanometers. Let's solve for lambda 2. The lambda 2 goes up, the 1.54 goes down, and what do we get for the value of lambda 2? 351 nanometers. We know that that number is going to be smaller than the first wavelength, and sure enough, it turns out to be smaller, so odds are we've done it correctly. Let's take a look at 15 here now. We want to draw the ray diagram that we've drawn in class here the very first day that we started doing these lenses here. It's a converging lens, so it's going to look like this. Our focal length is here. We'll say 2f is right here. We've got our object that is located at 2f. So if f is there, then the equivalent of f is over here, and the equivalent of 2f is over here. Here's our object at that spot that's equivalent to 2f. The first ray is going to go parallel to the principal axis, down through the focal point. Second ray is going to go down through the optical center, and it keeps going straight through. The image is going to be formed right here where these two rays intersect. What are the characteristics or the attributes of this image based on this ray diagram? It is larger, smaller, same size. Same size. Upright or inverted? Inverted, and it's real or virtual? Real. Could be projected onto a screen. We know that because it's solid lines that intersect. Why isn't the focal point in front of it? Okay, that's a good question. We draw it with a little dot over here in the same position as the focal point is on this side, right? But that's not really a focal point. That's just what we use as, we call a spacer. It basically says, okay, look, if we put the object right here versus right here versus right here, we get different characteristics. So we need those spacers just to tell us where the boundary is between the changing characteristics. Now, why isn't the actual focal point right here? Well, because rays that are parallel to the principal axis don't go through there. We define the focal point as the place where rays that are parallel to the principal axis all converge. Let's redraw that again. If I've got my converging lens, this ray that is parallel to the principal axis goes down here. It physically just goes down there. So, why doesn't it go down here? Well, because it's got to go through the lens. It doesn't reflect. Why doesn't it bounce off? Because it's a lens. Okay, if it's a mirror, it bounces off. But if it was a mirror, it would bounce off this way, right? Okay. So physically, this ray goes through this spot right here. Physically, this ray goes through this spot. Physically, this ray goes through this spot. So because all rays that are parallel to the principal axis go through there, we define that as our focal point. Let's take a look at 17 now. 17 says red light of 700 nanometers and blue light of 475 nanometers are both incident on a lucite block. Which color will be refracted to a greater extent? This goes back to when we first introduced refraction. We talked about a phenomenon called dispersion. You guys remember what dispersion is? I'll give you a little hint. Pink Floyd. No, that's diffraction. Why am I saying Pink Floyd? Because of the album cover, yeah. When we have white light that strikes that prism, that white light splits up. We get a little bit of splitting up right here inside the prism, and then it splits up even more on the other side. Now, why does it split up? Well, it splits up because the index of refraction for this lucite, or whatever material it is, lucite, glass, plexiglass, whatever, it doesn't matter. The index of refraction is slightly different for each different wavelength or each different frequency. In other words, each different color. Each different color of light will therefore refract a different amount. Therefore, when we have white light that combines all the colors of the rainbow, it ends up splitting up because all those colors bend a different amount. Now, which one bends the most? Which one bends the least? Which one do we have at the bottom? Which one do we have at the top? Red at the top, violet down at the bottom. In other words, red light that has the smallest frequency, that has the biggest wavelength, will cause the smallest index of refraction. Violet light that has the biggest frequency, the smallest wavelength, will cause the biggest index of refraction. It will therefore bend the most. Let's go back to our question here. Red light 700 nanometers, blue light 475 nanometers. Which color will be refracted to a greater extent? It's going to be blue light, right? Because this material has a higher index of refraction for higher frequencies or lower wavelengths. Yep. Mathematically? No. No. Not unless you knew the index of refraction for lucite for these different colors. Oh, did they? Where do they give you that? Okay, be careful though. That's still not enough. Okay, Courtney said, Courtney's question is a good one. Said, is there any way to do this mathematically? And I said, only if you have the index of refraction for lucite for both blue light and red light. Here we have the index of refraction for lucite. We're assuming it to be a constant index of refraction. Well, it's not. It's different for blue light than it is for red light. Okay, you're given one value for the index of refraction here. If you're going to do question number 17, you have to have two values. And there are two values. They're not very much different, but there are two different values, one for blue light, one for red light. Okay, we assume in most cases that it's just one value, 1.52. But for this question, we'd need to be more precise and know both of them. No, we can see that the blue has a shorter wavelength already, right? You would see that the blue would have a larger angle of refraction. If it bends more, it's going to have a bigger theta 2 than red light will, right? Honestly, the easiest way to do that is to remember it. Yeah, picture, the diagram. Okay, I don't memorize the answer to that question. Okay? I've got to take 5 seconds to think about that when I read that question every single time. Even if I've seen that question before, I've still got to take 5 seconds to think about it. I just picture the diagram. Okay? I picture the rainbow that comes out of this prism. Okay, I can see it in my head right now, literally, and I can visualize the red light on the top and the blue light on the bottom, or violet light on the bottom, indicating that blue light refracts more than red light does. All right, finally, question number 18 says the focal length of a converging lens in a computer projector is 8 centimeters. An LCD panel is positioned inside the projector and serves as the object. We want to find a number of things based on different scenarios here. It's a converging lens, so we're going to circle converging and write down the focal point is a positive value. Okay, and its value is, of course, 8 centimeters. F is 8.0 centimeters. The LCD panel, which is serving as our object, is located 8.1 centimeters from the lens. Tell me what that represents. If our LCD panel is that far from the lens, that's going to be our object distance. It's going to be DO. Good. We want to see how far away the screen should be placed so that a clear image is produced. What are we looking for there? How far away the screen should be. That's going to be the image distance, right? In other words, where is the image going to be formed? Well, that's where we want to put the screen. So we're looking for DI in this case. Okay, we also have the LCD panel is 1.75 centimeters high. That's going to be HO. We want to look for HI. The screen is now moved 3 meters closer to the projector. How far must the object now be from the lens in order to generate a focused image? Okay, let's deal with A and B, because C is a bit of a tougher question. So even though we were only asked for C, let's do the whole thing here. Okay, and then we'll go to C in just a moment here. Let's find DI first. Let's use the lens equation. 1 over F is equal to 1 over DO plus 1 over DI. 1 over 8 is equal to 1 over 8.1 plus 1 over DI. Does anybody have the value for DI there? 648 centimeters, okay, or 6.48 meters. Okay, good. Let's find the value of HI. We're going to say HI over HO equals negative DI over DO. Does anybody have the value for HI now? Negative 140. We got an image that is quite a bit larger than our object is, which we would expect if we're projecting an image onto a screen by an LCD projector. It's upside down, which we expect to happen, because we talked about that, right, when we do our ray diagrams. Now let's do C. If the screen is moved 3 meters closer to the object, how far must the object now be from the lens in order to generate a focused image? What we're going to do in question C is change our image distance. If our image distance was 648, now our image distance, DI, is going to be 348. Look, if I'm moving the screen 3 meters closer, then that better be where the image is formed. 3 meters closer, 348 centimeters. Now what I'm looking for is DO. Where do I have to put the object in order to get the image at that spot? Does F change? Does the focal length change? It's the same lens, right? Good. It's the same lens, so we're going to leave the focal length here as 8.00 centimeters. So the trick with this one really is recognizing those givens. We're going to say 1 over F is equal to 1 over DO plus 1 over DI. And we're going to say 1 over 8 is equal to 1 over DO plus 1 over 348. Does anybody have a value for DO doing it this way? 8.19 centimeters. So you can see here, to change the position of the screen by quite a bit, we don't actually have to change the position of the object by all that much, right? 9 centimeters. I mean, 9 centimeters is still 9 centimeters. Inside a projector is still quite a distance. But compared to how much we're changing the position of the image by, it's not all that much. Good? Any more questions for those homework questions? All right, let's go back to our diffraction thing for a minute, and then we're going to try to get into just a little bit of mathematics with this here. Diffraction, if you remember from yesterday, was the spreading out of a wave versus refraction, which was the bending of a wave, versus actually dispersion. Dispersion, which is a form of refraction, but it's the splitting up of the light due to the refraction of different colors. at different amounts. So diffraction is spreading out. We have a barrier, we have an opening, the wave goes through that, and it spreads out around it. That's why when you stand around a corner, you hear somebody. You hear their voice when they yell your name, because their voice, sound waves, goes around that corner. It spreads out. It doesn't just travel in a straight line. It spreads out as it goes around that corner. We said that when we have diffraction taking place from two openings, then we get a phenomenon called interference taking place as well. Both diffracted waves interfere with each other, producing various areas of constructive interference and destructive interference. If we're talking about the diffraction and therefore interference of water waves, then we're going to get these areas of big crests and big troughs, constructive interference. We're going to also get areas of complete cancellation of the water wave. That's destructive interference. So constructive interference lines, big crests, big troughs. Destructive interference lines, no crest, no trough, because they completely canceled each other out. But if we're talking about the interference of light, we can't see these lines unless it's reflecting off of something. Maybe if you've got dust in there or something, maybe you see a little bit of reflection. But for the most part, you're not going to see these lines of constructive and destructive interference. So what we have to do is introduce a screen up here. On the screen up here, we'll detect the areas of constructive interference as bright spots. And we'll detect the areas of destructive interference as dark spots, no light, because the light is completely canceled out. What we end up getting is a bright spot, then a dark spot, then a bright spot, then a dark spot, and so on both sides. Does that ring a bell from yesterday? Now, if we plot a graph of the intensity of that light as a function of the position, so in other words, if we look at that screen that we had on our last page here, the position along, we'll call it along the x-axis here, this light is going to be a little bit more intense than this one. Okay, so when we plot a graph of that intensity versus its position, it's going to look something like this. These should be kind of curved at the top, though. You can see that in the middle, we've got the highest intensity. As we go away from the middle, we have intense light, and then we have no intensity. That's a dark spot. Then we have intensity again, which is a bright spot, and then we have no intensity, which is a dark spot, and then intensity, which is a bright spot, and so on and so on and so on. That middle bright spot we call the central maximum. Central because it's in the middle, maximum because it's a bright spot. Another term for that could be the central bright spot, the central maximum, the central bright spot, the central antinode. The next one we see on the right side or the left side, okay, it's symmetrical. Both sides are named the same. We're going to call the first order maximum. So this would be the first order maximum, the second order maximum, the first and second order maximum on the other side. Now, that first dark spot we call a minimum. The minimum could be also known as a dark spot. It also could be known as a, not an antinode, but a node. This one we're going to call our first node, or our first dark spot, or our first order minimum, our second order minimum, and third order minimum, fourth order minimum, and so on. First, second, third, fourth on the left side. Again, symmetrical to the right side. Now what I want to do is identify in this whole scenario of light diffracting and therefore interfering, producing an image on a screen of this bright spot, dark spot, bright spot, dark spot. I want to identify some different variables that you're going to see in a couple equations that we're going to see in just a moment here. So let's draw a bit of a different version of what we've just seen. Here's our two openings. The light is going to go through both of those openings. It's going to diffract through both of them. It's going to interfere. it's going to produce an interference pattern on this screen up here. That interference pattern will be like this: bright spot, dark spot, bright spot, dark spot, bright spot, dark spot, and so on. Same thing on the other side. There are a number of variables that can be a little bit confusing here that we have to label on this diagram. The first variable that we're going to label comes from the first equation that we see that describes this. The first variable that we're going to label is d, little d. Little d is going to represent the distance between the slits, or the distance between the openings. Well, that's not overly hard, right? Let's identify L now. D is the distance between the openings. L is going to be the distance from the openings to the screen. Now it gets a little bit more confusing because now we've got two different distances. One that is going to be pretty small, that's D, the distance between the slits, and then one that's going to be quite a bit larger, which is going to be L, the distance from the slits to the screen itself. We've already identified D, I guess. Now let's identify X. This is the toughest one. X. X could be this distance, the distance between two maxima. It could be this distance, the distance between four maxima. It could be this distance, the distance between a minimum and a maximum. It can be any distance you want between any maximum and any other maximum, or between any minimum and any other minimum, or between any maximum and any minimum. How can it be any number you want? Well, you're going to see in a second, there's another number that can be any number you want as well. You just have to be consistent between those two numbers. Doesn't matter which ones you use, as long as you're consistent between the two of them. So X is going to represent the distance between any maximum or minimum and any other maximum or minimum, whatever happens to be convenient for you. Theta is going to represent the angle between the central maximum and some other maximum or some other minimum. Theta can't be any angle you want because it's always measured from the central maximum, unlike X, which can be measured from any maximum or any minimum to any other maximum or minimum. Theta can be measured to any maximum or minimum, but it's always got to be measured from the central max, from the middle bright spot. No. It's going to be two different equations. X and theta are not going to appear in the same equation, so it doesn't have to be the same max or min as you got for X. I mean, if you look at that, X doesn't have to be measured from the central, right? And theta does. So those two don't have to be consistent with each other. But the next number does have to be consistent with either theta or X. The next number is N. N is the difference in the number of maxima that's encompassed by either X or by theta. So for this one up here, we'd make N equal to 1 because we're dealing with the first maximum and the second maximum. 2 minus 1 is 1. This one, we're dealing with the central maximum. We'll call that 0. And the 1, 2, third order maximum, we'll call that 3. 3 minus 0 is 3. Here we're dealing with the second order maximum, And the first order minimum, n would be what in this case? Tough one. Anybody think they have that one? It's not 1, because n is equal to 1 when we're going from the first maximum to the second maximum. Not 0.5, but you're getting close. We got numbers all over the place here. N is going to be equal to 1.5. 1.5. This is 0. This is 1. This would be like saying, it's not a maximum, but if we pretend it is for a second, it wouldn't be the first maximum. It would be the 0.5, 0.5, however you say that, the 0.5 maximum, right? What's 2 minus 0.5? 1.5. So n is going to represent the difference between the maxima or minima. What would n be in this case? When we're going from 0 to the first order maximum, n would be 1 minus 0 is 1. What would it be in this case when we're going from the central maximum to the second order minimum? N would be 1.5, right? It would be 1 if we were going to here. It would be 2 if we're going to here. It's 1.5 if we're going somewhere in between. All right, it's a little bit confusing, all these different variables, and a little bit tricky to keep them straight, but does it make sense? I'm not asking right now if I had a quiz, would you remember what each of these mean? Okay? Of course you're not going to remember all of these right now, but does it make sense? All right, our two equations look like this. D sine theta over n is equal to lambda, that's the wavelength of the light, and lambda, the wavelength of the light, is equal to xd over n times L. This equation is always valid. This equation is usually valid. I'm going to put a little disclaimer by that, though. This is valid.
Diana Atkinson, calling station 102, please.
Valid at small angles. Essentially, we have a small enough angle to make this valid if x is less than 10 times L. If x, how do I say that? How do I say that mathematically? Basically, if we multiply x and we get a number that's less than 10 times the length, 10 times L, then that equation is valid. Does that make sense? How do I write that mathematically? If 10 times x, if L is not more than 10 times x, then we should be good to go. If L is not more than 10 times x, then we should be good to go. And in the vast majority of cases, that will be the case. So both equations would be valid in the vast majority of cases. Good news, we didn't get to a single sample problem, which means no homework. Have a good weekend, everyone.